Well, hello there. My name is Chris Fregley, and I'm here with my co-presenter Philip Schmidt, and together we're going to talk about foundation models and blueprints for success. Real quick, my name is Chris Fregley. I'm a principal solution architect at AWS. I focus on generative AI. My co-presenter Philip Schmidt, he's a technical lead at HingFace, also a AWS ML hero. I've known Philip for quite some time now. Philip has probably one of the best blogs on SageMaker and generative AI and Hugging Face. And I recently finished a book called Generative AI on AWS with Philip's help also as well. He was a reviewer of the book and someone we trusted very highly for this effort. So together today, we're going to discuss 5 topics. We're going to start by talking about generative AI foundation models and sort of what they are and where they fit in today. We'll talk about how to train these foundation models with purpose-built hardware on AWS. We'll also discuss how Hugging Face makes training those models on the purpose-built hardware much, much easier with a library called Optimum Neuron. We'll show some of these code examples for the Optimum Neuron library, and then we'll wrap it up by choosing the right generative AI model and architecture for your use case. So let's start with the generative AI foundation models. Where are they being used? The short answer is these days they're being used pretty much everywhere, from search to customer service to trying to analyze data to creating digital assistants to help us with just daily tasks. So here's some options to actually use these foundation models on AWS. You can actually deploy Hugging Face models directly from the Hugging Face community, from the HingFace Hub on AWS using something like SageMaker, Amazon SageMaker. Sometimes this does require a bit more expertise and a little bit more configuration. And so the other option that's very popular is to use Amazon Bedrock. So Bedrock is an API where you have access to many, many third-party models and makes it really easy to integrate with your application. With Bedrock, you can also fine-tune models. You can do what's called continued pre-training and just continue to add more and more data, more and more PDFs, more and more documents, and make these models specific to your use case. So this is sort of the larger landscape of the generative AI stack within AWS. And really this talk is going to focus more on the bottom, which is the infrastructure for foundation model training and for inference. And specifically, we'll be covering the purpose-built hardware Trainium, Inferentia, and talking about the Neuron SDK in the bottom right, which is used on top of that custom-built hardware. So here it is, purpose-built hardware, AWS Trainium and Inferentia. So Trainium, as you could tell by the name, is used for training these models, fine-tuning them, or training from scratch. There's huge cost savings by using this purpose-built hardware on AWS. Also, when you go to actually serve the models in production to support your applications, you could use either Inferentia Generation 1 or the AWS, the Inferentia version 2. And there's super high performance and much lower cost if you go with these purpose-built hardware options. Here's some of the customers using these. So you see a lot of very familiar names on here. Also, there is quite a lot of community and partner support for Trainium and for the Inferentia. And so we see PyTorch is on here, OctoML, the Ray project. We have Hugging Face, of course, who is going to take over this talk in a bit. Here's some of the instance types for Trainium. And there's 3 of the instance types listed here with different characteristics. Keep an eye on the network bandwidth. So if you see the TRN1N 32XL actually has 1.6 terabit of network bandwidth between those instances, which is very powerful and a number that you want to keep an eye on when choosing the type of instance that you're going to use, especially at scale when you start going beyond one single instance. Now, on the inference side, when you're actually serving these models to your applications, there's a few different options for the Inferentia 2 chip. And so here we see 4 different instance types. We see the total aggregate of the accelerator memory. We see the networking and the number of chips on these different instance types. And of course, you want to size these based on the workload, based on the amount of throughput that you're expecting and the latency, and of course, cost. And so here we see some really good numbers that are relative to other options. So 90% higher throughput per dollar for diffusion models. This is going to be your stable diffusion, some of those familiar names for those model types, and then also much lower latency as well too. All right, if you're interested in getting started with these chips, you can certainly go launch one of the instance types. You can do this through SageMaker Studio, for example, and launch a notebook on one of these Trainium instances. You could also, of course, spin up an EC2 instance and shell in there and start writing the code. We'll talk in a bit about the Neuron SDK. That's the software development kit that abstracts away this hardware. And the other thing you'll want to get familiar with is how to monitor, tune, and scale these workloads in a way that you're used to doing with commands like top and other commands to look at the processes that are running, the accelerator utilization, and that type of thing. So let's dive a bit into the Neuron SDK. We'll see there's actually a few different components to this SDK. There's the lower level libraries, as well as the framework support, so PyTorch and TensorFlow that we mentioned before. There's also what's called the Neuron compiler. This is going to take your model and compile it down to this chip. And as you'll see in a bit here, Hugging Face has created what's called the Optimum Neuron library that makes all of this super simple in just a few lines of code. And so there's the Hugging Face Optimum Neuron library and the fun Hugging Face logo. And I'm now going to turn it over to Philip. And Philip, take it away.
Thank you, Chris. So Hugging Face and AWS, what does it mean? To make it simple, we have created a formula. If you take Amazon SageMaker, AWS Trainium or Inferentia and multiply it with Hugging Face, you get state-of-the-art models in production powered by open source for generative AI like Llama, Mistral, Stable Diffusion, BERT, Roberta, or all other models. But before we take a closer look at Hugging Face Optimum Neuron and how that works, let's start with who or what is Hugging Face. So for the one of you who haven't heard about Hugging Face or are not familiar with what we do, we are an open platform for building the AI community and GitHub for machine learning. Our mission is to democratize good machine learning and make it accessible to everyone. At the heart of our open platform is the Hugging Face Hub. Here users can find, search, filter hundreds of thousands of models from traditional transformers like BERT or the latest generative AI models like Llama and Mistral. But the Hub not only hosts models, we also host datasets and spaces. Similar to models, you can search and find the best suited dataset for your domain or use case, which makes it easy for you to get started with building or fine-tuning your models. And spaces? Spaces are machine learning demos. You can directly try for free in your browser. Spaces have become over the last year the central place for researchers to launch their work and models. Spaces makes it super easy for you as a user to try out generative AI. There are many examples like generating images with Stable Diffusion or chatting with Llama. Spaces are free for you to get started. You can choose from Docker templates or build with Gradio or Streamlit. With all that, what do you need to work together? Right, collaboration. Similar to GitHub, you can have discussions on any repository from models to spaces, open pull requests, ask questions, or just fork a demo, improve it, and share it again with the community. The second pillar of Hugging Face is its vast and open source ecosystem. Without open source, we wouldn't be able to do what we are doing. Only through open source, we can enable companies to benefit and use all of the models and datasets. For example, you can use transformers and datasets to train your models, diffusers to generate images, or Gradio to build your demos. Open source only works if you work together, and at HingFace we would be nothing without our community. By connecting researchers, developers, and enthusiasts, we can foster an open and transparent way to collectively improve and build OpenAI. And lastly, there's our product and partner ecosystem, where we, for example, collaborate with AWS to make it straightforward to put generative AI into production. Whether you need cloud services, specialized hardware, or robust endpoints, we've got you covered. Let's take a closer look at the HingFace Hub. Here you can see the model overview of the most trending open models. This page you will find if you go to hingface.co/models. This is also the slide we need to change the most frequent, since numbers are always out of date. As of this week, we have crossed 100,000 public datasets. We now host over 200,000 public demos and over 400,000 different open models, and crossed over 1 million daily downloads for models and datasets. Each of the overview is a datasets or models has filters on the left side, which you can use to find more easily what you are looking for. For example, you can filter by task like image generation, text classification, and even multimodal tasks like image to text or text to image generation. You can filter models and datasets by language or even license if you're worried if you can use your model in production or not. The models overview is also a good way to keep yourself updated since it's sorted by the trending models. HingFace is built on open source, and our open source ecosystem is growing vastly. We are amongst the top 30 organizations on GitHub. You might know about popular libraries like transformers and datasets, but we have a lot more to offer. TRL, for example, stands for Transformers Reinforcement Learning, which lets you apply RLHF or alignment methods like DPO on transformers and diffusion models. PEFT, or Parameter Efficient Fine-Tuning, which supports methods like ULoRa to reduce the needed memory for fine-tuning LLMs. Or Gradio, which lets you easily build UI applications with Python. And of course, there's Optimum. Optimum is what lets you use transformers easily on AWS Inferentia and Trainium. To give you a feeling of how fast and performant generative AI is on AWS Inferentia, we have created 2 dedicated spaces to run Llama 7B and Stable Diffusion. You can go to HingFace on the shown links and give it a try. We also have published blog posts and guides on how you can set up those yourself. With Llama, you can chat, for example, asking questions about AWS and how Inferentia works, and with Stable Diffusion, you can generate images, for example, of a graffiti of a robot serving meals to people. Looks super cool, right? All of the demos are built with Gradio and Optimum Neuron. Optimum Neuron is the interface between HingFace Transformers and AWS Inferentia and Trainium. Optimum Neuron is built on top of the AWS Neuron SDK, giving you the Transformers experience you might know from GPUs, but for Inferentia and Trainium. Together with AWS, created tools to easily compile, train, and deploy Transformers and diffusion models on AWS accelerators. As of today, we support popular transformer models like BERT or Roberta, as well as LLMs like Llama or Mistral, and of course, diffusion models like Stable Diffusion and Stable Diffusion XL. If this makes you excited, you can go to hingface.co/docs/optimumneuron, where you can find our documentation, which helps you get started, includes dedicated tutorials on how to fine-tune BERT, generate images with Stable Diffusion, or train and deploy in Llama. It also includes guides on how you can set up your own environment, explains you how distributed training works, or the Neuron Model Cache, which is something unique we have built together by caching Neuron models directly on the HingFace Hub. There's no additional need or cost for compiling your models again. Now let's look at some practical examples and code, starting with generating images. Using Stable Diffusion on AWS Inferentia is as simple and as straightforward as using it with GPUs. You need to import the Neuron Stable Diffusion pipeline from Optimum, then load your compiled model from HingFace with the from pretrain method, and then you can start generating images by providing a prompt. Here's an example on how to generate a high-resolution image for an astronaut in a jungle. You might wonder, why did he say compiled model? AWS Inferentia or Trainium require us to compile models ahead of time. This means we need to export a regular transformer model to Inferentia, but that's super easy and straightforward since we integrated the export and compilation directly into the Optimum CLI, or you can use it with code. Similar to Stable Diffusion, we can easily deploy LLMs from HingFace to AWS Inferentia. As you now know, the first step is to compile our model. Optimum not only offers the CLI to do that, you can also use code to load and compare a vanilla transformer model to be compatible with AWS Inferentia. Therefore, we have to define our input arguments and compile arguments. Those define where we want to run the model. Here, for example, we set the num cores to 2, which indicates that we have 2 neuron cores available. So, for example, the AWS Inf2 X-Large instance comes with one Inferentia device, which has 2 neuron cores. We also need to define our input shape, since AWS Inferentia currently only supports static shapes, meaning we need to tell the compiler in advance how our input is going to look. And we set, for example, a batch size to 1 and a max sequence length to 2048. This means during inference, our input can only be a batch size of 1, meaning we cannot provide 2 inputs at the same request. And the max sequence length is 2048. So if we have a longer sequence length, like 3000 tokens, we need to recompile our model with our new configuration. To compile the model, we simply can use the same neuron model class for kosher language modeling and make sure we set the export value to true. This will now load the traditional transformer model, compile it to Inferentia using our compile args and input shapes. In our example or code snippet, you can see here we are loading the official Llama 2 chat 7b from Meta, exporting it with our compile arguments and input shapes, and then we are saving the model to disk into a Llama neuron repository where we can then load the model again. But also after compilation, you could directly use it to generate new text. And for generating, we can either use the model from a local disk, as shown here from Llama Neuron, or we can load precompiled models from HingFace directly. So in addition to regular transformers models, we also collaboratively with AWS precompile popular LLMs and make them available on the HingFace Hub. This allows you to directly load the model and skipping the compilation part, since compiling LLMs takes, especially the bigger ones, up to 60 minutes for a single compilation. And to make it easier for you to get started, we pre-compile those models. So once we have our compiled model, we can use it with the from pre-trained method. Here, since we already exported it without the export true argument, we then load our tokenizer so we can tokenize the text input into tokens. For our inference, we have a prompt. In this case, what is deep learning? Then we tokenize our prompt into tokens, make sure that we return PyTorch tensors, and then we can simply use the same model.generate method you know from transformers, providing our generation arguments with max new tokens, sampling method, temperature, top K and top P, which will then be used to generate our tokens. And with the batch decode method, we can convert our tokens back into a text, getting us the output. What is deep learning was our prompt. And then the output is the term deep learning refers to a type of machine learning that aims to model high-level abstraction of data in the form of hierarchy of multiple layers of increasingly complex processing nodes, which sounds correct to me. Similar to inference, you can train models directly on, this case, AWS Trainium. And to make training easy, we created a brand new neuron trainer for AWS Trainium and Inferentia, which abstracts away all of the heavy lifting required to fine-tune model. Since Llama is a pretty big model, it will not fit on a single device. Therefore, we added support for tensor parallelism and pipeline parallelism, which allows us to shard and distribute the weights and optimize the states across multiple devices. We load our model using the lazy load for parallelism context with our tensor parallelism size, and in there we use the normal transformers auto model for kosher language modeling class with our model ID. In this case, we are going to fine-tune again Llama 7b, but not the chat version, the base version. And before that, we set our pipeline parallelism size of 2 and tensor parallelism size of 8, which will then be used to shard our model correctly to the two different sizes. Afterwards, we define our training arguments, where we need to set our pipeline parallelism degree, and in the tensor parallelism degree, we can enable sequence parallel and 0-1, which saves us additional memory, meaning we can run training on a bigger model on a smaller instance or have faster training time. Then we only need to create our trainer, where we pass in our model, our data set, our training arguments, and eventually our evaluation data set, and we can then call trainer.train. And the whole script will then be executed by torch run, providing the number of neuron cores or Trainium devices we have available. And then the trainer will automatically distribute our model and data set to all different accelerators and runs distributed training on our machine. And what is super nice about it, we directly integrated it into Amazon SageMaker, using the benefits of Amazon SageMaker to scaling up your training onto multiple nodes or multiple devices, meaning you can write a single training script for Llama 7B and automatically scale to Llama 13B or 70B by simply adjusting your Amazon SageMaker training parameters to select more instances or bigger Trainium instances. So now we know how to deploy and train generative AI models, but where do we start? What's the best model to start? What other models are available? Open source AI is a fast-moving space. With new models released every month, it is hard to keep track of what's the best model, how are other models performing. For this, we created and maintain two open leaderboards on HingFace. One is the Open LLM leaderboard, which evaluates and ranks different Open LLMs on 6 different benchmarks, including MMLU, TrueFull-QA, Vinograde, and HellerSwag. And then there's the MTEB benchmark, or Massive Text Embedding Benchmark leaderboard for embedding models. On the Open LLM leaderboard, we not only include base LLMs, so LLMs normally come in like 3 different flavors, so to say. We have base models, which are only pre-trained, meaning they can complete text. Then we have fine-tuned models, which are fine-tuned to fulfill certain instructions, like as we have seen earlier with what is deep learning, we get back a response. And then there's also a new class or type of models which are trained using reinforcement learning through RLHF or DPO. All of those 3 different categories are available in the Open LLM leaderboard, meaning you can compare base models with fine-tuned models, or fine-tuned models with fine-tuned models, or RLHF models with RLHF models. What's nice about the Open LLM leaderboard is you can filter different model sizes. So if you have a given budget for your project or for your use case, you can select, okay, I can only run a 3 billion parameter model, I can run a 30 billion parameter model, and then the Open LLM leaderboard will automatically filter out all models outside of your range. This makes it super easy for you to get started by selecting the right model for your task and for your budget. And similar, the MMTEB leaderboard is for embedding models, which are now commonly used in generative AI application for creating RAG pipelines. So an embedding model is used to convert a text into a vector representation, and then you can find similar documents for it. And it's super helpful since the MTEB leaderboard includes not only English as a leaderboard language, we also have multilingual leaderboards inside MTEB, which allows you to select the correct embedding models for your language. You can find both leaderboards on HingFace. Both are spaces, as we learned earlier, easily and free accessible for you, and you can search and filter there. At the end, let's take a quick look at a reference architecture for building RAG applications using open source and AWS accelerators. A typical RAG application uses at least 2 models, one embedding model and one LLM. The embedding model, as we heard, is used to create a vector representation for our documents, and the LLM can be used to rewrite our user input, generate responses, or rank different documents getting back from the embedding leaderboard. Here we created together an architectural overview of how you would implement a RAG application on AWS, leveraging Amazon SageMaker, powered by Inferentia and HingFace model. We have on the right side our document ingestion pipeline, where users can either upload documents directly onto an S3 bucket or through an API gateway, which are then triggering an AWS Lambda function, which calls our embedding model. The embedding model then takes the document and creates a vector representation of it and stores the vector representation in Amazon OpenSearch for search later. On the left side, we have our customer-facing or user-facing pipeline where users or clients can directly access our RAG pipeline via API or through a frontend, which is hosted through Amazon CloudFront and S3. The frontend provides an API, which also is connected to an AWS Lambda function, which receives the user input. So for example, if we stick with our what is deep learning question, the deep learning question comes in, is then again embedded using the embedding model, and then we go into OpenSearch trying to find similar documents. So if our company has documents explaining how deep learning works or have a specific document on like which deep learning architectures are used, those documents are then retrieved using a nearest neighbor algorithm with our embedded query and returning top 5 documents, for example, from our OpenSearch cluster, which are then used to create a unique prompt for our LLM. The prompt then could look like similar. We have our question with what is deep learning, we have a context with deep learning is, and then a lot of information. And then the LLM will generate a correct response using the provided context in our question. Thank you for joining our session. Make sure to follow Chris and me on social media. And if you have any questions or are curious about a certain topic, feel free to reach out to us. And don't forget to complete the survey. Bye.